from the radar station to the plane is changing at exactly the moment that the distance, that it's 5 miles from the radar station. Let me see, that's 5 miles away from the radar station. So I want to know that at exactly the moment z is equal to 5 miles. So this is my general picture, what's happening. My instant in time has this. I have my distance is 5. This is 2. Here's my plane. Here's my radar station. And because I know 2 of the 3 sides of a right triangle, I can solve for this side. So I'm going to call that x, right? I know x squared plus 2 squared must equal 5 squared. So x squared plus 4 must equal 25. That means that x squared equals 21. So x is the square root of 21. So that's the instant and time also. I know that this is root 21. Now, let's try and come up with a relationship between x and z. And from my general picture, we can see here, again, the Pythagorean identity. We know a squared plus b squared equals c squared. So I can say that for this problem, x squared plus 2 squared, which is 4, must equal z squared. And now I can differentiate with respect to time, get 2x dx dt plus the derivative of 4 is 0, so I don't put anything, and 2z dz dt. Now, x at the moment in time, so now I'm ready to fix everything, is root 21. dx dt is how fast the plane's moving, which is 450. Was it 450 or 540? 540. Oops. 540. That must equal 2 times now z at the moment in time is 5. And then dz dt is what we want to know. So let's see. I'm going to cancel these 2's. Divide both sides by 5. So I can take that 540 and I can divide that by 5. I get 108. So 108 times root 21 should be the rate at which the distance between them is increasing. If I take 108 times the square root of 21 as a decimal, this is approximately 494.92 is dz dt. And that's measured in miles per hour. So that's what we're looking for right there. All right, let's just check it real quick. Right here, 108 times root 21, about 495 miles per hour. All right, which one am I? Quick little break here. All right. Taking a look at this one. A street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 7 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? So let me draw this picture. Information again. We have a 15-foot pole, 6-foot man. His speed is 7 feet per second. 15-foot pole, 6-foot man. So let's say this is our pole. Here's our light, right? It's giving off light. And it's 15 feet. That should not change. Then we have a man. And he looks weird. And he is 6 foot tall. And he is walking away from the pole at 7 feet per second. So he's moving in that direction. And as the light shines, right, hits him and his body makes the shadow of himself on the ground, which is going to be something like this. It's a shadow on the ground. So we have basically from the tip of his head down to his shadow like that. So we want to know how fast the tip of his shadow is moving, which is that point right there. We want to know how fast is it moving to the right. And we'd like to know, do we want to know that at a particular point? Let's see. How fast is the tip of the shadow moving when he is 40 feet from the pole? That will be our instant in time. Okay, so let me talk about some variables here. This is going to be my general picture. Everything I've put on there is in general. I mean, the 15 feet doesn't change, 6 feet doesn't change. His speed he's walking doesn't change. And then what we want to know is how fast the tip of the shadow is changing. So I know that the distance from the pole to the man I can call x. And we know that dx dt, because he's walking away at this rate, 7 feet per second. So that's how fast x is growing. And then the distance from the pole all the way to the tip of the shadow, we will call s. And therefore, we want to know, so this is what we're given, we want to know what ds dt is. And we want to know it at exactly the point that he is, what was it, 15 feet? 40 feet from the pole. So we want to know that exactly when he, which is the man, is x, is 40 feet from the pole. Okay, so what I need to do is find a relationship between x and s. So what you need to see here is that we have a set of similar triangles. Now, I never put the instant in time picture, so let me do that. Okay, 15's here, the man's walking, that's 6. I want to know what's happening when he's 40, right? That's the picture. X is 40 at that instant in time. The question is, you know, what's S at that instant in time? We're going to have to figure that out. But let's try and figure out what the relationship is. What's the relationship between X and S? So I'm going to take my general picture here. I'm going to draw it again down here so we can see it. This, right triangle 6. This distance right here is X. This is 15. This distance right here is S. So we actually have two triangles here. We have a bigger triangle. Okay, that's this outside one. Okay, that's 15. And this side is S. Looks like a 5. S. And then we have a smaller triangle, which is this one, like that. And that triangle, this is always 6. And then this side down here will always be whatever S is, that's the whole way, and then take away S. So if you subtract S, this right here, this piece right here will always be the S take away X. So I'm going to say S take away X. Now the reason I've done this is because these triangles are what we call similar triangles, meaning that this angle and this angle are the same. They both have the same right angle in it, so that means these are the same. So they're similar triangles. So what that means is that if you have similar triangles, the ratios of the sides are equivalent. That means I can take 15 divided by S and say that that's equivalent to the 6 divided by S minus X. And now what I have is an equation that has S in it and X, and that's what I was looking for. So I'm going to work with that equation, and let me bring it back up here. I'll just put it right here. It was 15 over S is 6 over S minus X. Now I'm not going to start differentiating yet. I'm going to try and clean this up a little bit. So I'm going to multiply both sides by S. That'll get this to cancel. And then I'm going to multiply both sides by S minus X. We're basically cross-multiplying. And then now what I'm left with is 15 times S minus X equals 6S. So 15S minus 15X equals 6S. And if I subtract 6 from both sides, I get 9S and I move the 15x, negative 15x to the other side. And so I get S is equal to 15 over 9x, reducing that fraction. What goes in 3 goes into both of those, 5/3 x. So S will always be 5/3 x. And now I can take that and I can differentiate that with respect to time. So derivative of the left side is ds dt. Derivative of the right side, we have a constant, and then derivative of x is dx dt. I know what dx dt is, right? I know what dx dt is. It is 7, and then ds dt is what I want. So if I just plug a 7 in here, right there, then I'll get that ds dt is equal to 7 times 5, which is going to be 35 over 3. And now S is actually a distance from the pole to the tip of the shadow, so it's measured in feet. And then time here is time, oh, whoa, sorry, what is going on? And then time here is measured in seconds, so feet per second. So that is how fast the tip of his shadow is moving, 35 thirds. So 35 divided by 3, 11.6666. So 11.7 feet per second, approximately. Let's see here. .35 thirds. There you go. Okay. I think 9 is very similar to the one I just did, and 10 is similar to the one I did a little while ago. So let me just show you the solutions to those. So 9, bring this up, and give you a second there to pause the video and take a look at that solution if you need to. Again, that's a similar triangle problem. All right, and the problem there for that one was this. And then number 10 was a ship problem. So let me, again, bring that up. Uh-oh, there it goes. That's an interesting problem there. Another set of relationships with triangles. Okay. Okay. Last one here. Water is leaking out of an inverted conical tank at a rate of 11,000 cubic centimeters per minute. At the same time, water is being pumped into the tank at a constant rate. The tank has a height of 6 meters, diameter of top is 4. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, then find the rate at which water is being pumped into the tank. All right, there's a lot going on in this problem. So let me start with a picture of a tank. It's a conical inverted cone. Let me see how much they give you as far as detail here. That's okay, but I think you got to see this problem. So start this out. I've got